Real quick before we get started, please silence your cell phones. Don't worry about taking pictures of the slides. This is going to be recorded. I might even re-record the VO for this because I've had so much fun hanging out with you all the last couple of days that I sound like this. Don't worry about taking pictures of the slides. I'm going to have a QR code with some links to a bunch of extra resources that I think are really, really helpful. Hopefully we'll have time for Q&A. If we don't worry. I'll be up in the dev lounge this afternoon starting at like 12:30. So we'll come up, we'll do some interpretive Unreal help. That'll be great. And don't forget to fill out your post-show survey. I don't know if a lot of people know about this. If you go into the CVen app and you go to your profile, there's that little survey button. Click that because the organizers of the show use that survey to figure out how to make the show better next year. Like, you know, maybe don't have a speaker who loses his voice on the first day. That's totally fine. That's great feedback. With that, let's get started. If we haven't met yet, my name is Matt Ostale. I'm a senior developer relations technical artist here at Epic Games. And right now I want to talk to you about virtually everything. Because there are a lot of virtual features in the engine. Textures, micropolygon geometry, shadows, assets, but that's a totally separate talk. And fundamentally, these features are meant to help make the most efficient use of time and memory, both time and memory on the GPU and your time and memory as developers. But what is a virtual? What does virtual mean? We kind of yada, yada, yada past this. We're like, yeah, it's virtual. Look at the textures, it's fine. But it's really important to understand what it means to virtualize something in order to make the most efficient use of these features and take full advantage of them. And the easiest way I can explain this is when we virtualize something, we create a sparse version of it, only the bits that we need, and we figure out the bits that we need based on a feedback pass. So imagine we've got like a book, like a PDF of a book, and we know how many pages are in the book, and we know what page the PDF viewer is looking at right now, page 100. And so instead of sending the whole book into the GPU to be rendered or looked up, we just send the page that we need and maybe the 2 pages on the other side, and we send those up to the GPU because those are the only bits that we actually need to render. Right? That's it. That's all it is. Figure out the bits that we need, send it to the GPU, leave behind the rest. But why? Why did we need to do this? Well, back in the day, we really only needed to send a few things to the GPU. Textures, static meshes, skeletal meshes, maybe animations. And that's all we really needed to worry about in memory. But then, as more graphics features came online, they had to fight for the same amount of VRAM because it turns out that the video memory that we have access to is not growing at the same rate as the stuff that we're trying to put on virtual memory. So now we've got features like distance fields and lumen and nanite and ray tracing and all of these things and shadows. All of these things are fighting for more or less the same amount of virtual memory or video memory. So if we virtualize a bunch of these features, we can limit the impact of each of these features on the GPU. So the first one I want to tackle, the really big one I want to tackle, is textures. So because those were for the longest time kind of the biggest offender on the GPU. So the tricky thing with virtual textures is they are not a default feature in the engine. You have to enable them. You have to go into project settings, go say, hey, virtual texture, enable virtual texture support. You have to have this all turned on in order to use it. And there are kind of 2 ways we can use virtual textures. But basically, virtual textures is going to take a big old texture, break it up into individual tiles, figure out what tiles we can see. So I've got a little visualization here for that. Thank you. And you can see little bits of tiles, and we go, okay, these are the tiles that are actually visible on the GPU. It's like we're MIPPing MIPS, right? Oh, if we can only see the bottom corner, we're only going to send the bottom corner up to the GPU. And one of the biggest memory benefits of this, so we're in the Hillside sample project for those unfamiliar. It's an architectural visualization sample, not necessarily like real-time 50 FPS, 60 FPS kind of thing. But importantly, from day one, they said this is going to be virtually textured. Everything is virtual textures. So what I've got pulled up here is stat streaming, and this is showing us the, what I've got here, the required pool. This is how many MIPS of non-virtually streamed textures that need to go onto the GPU. It's 100 megabytes, which is wild. This is a really beautiful sample. It's got a bunch of textures. That doesn't seem like enough, right? Well, if we go over to stat virtual texture memory, we can see we've got a total physical memory of about 423 and the page table memory of about 48 megabytes, so under 500 megabytes to store all of the textures for this scene. But the total disk size, so if we had all the MIP zeros of all these textures, if we just turned off texture streaming, it's 22 gigabytes. And we're able to efficiently use all 22 of those gigabytes to render this scene, which is wild. So there are a couple of options for virtual textures. We've got streaming and runtime. Streaming virtual textures save you memory at the marginal cost of performance, and runtime virtual textures save you performance at the cost of some video memory. We're probably familiar with these from landscapes, right? Okay. So streaming virtual textures is the one I want to talk about the most. This is, I think, the most important takeaway. If you take nothing else away from this talk, streaming virtual textures. Because I think this is underutilized, and I want to demystify it. And so we've already got it turned on in our project settings. All we have to do in the texture is go down to virtual streaming, right? Virtual texture streaming. That's going to give a little VT in the corner of the texture. That's totally fine. And then in a material, this is the basic surface material for this entire project. There is no option to not use virtual textures in this project, because when you have a texture object parameter or a texture sample or something like that, a virtual texture has to use virtual sampler types. So that's really all it is. You turn it on in the texture, you turn it on in the parameter, you're all set. But there are some things you got to think about, right? Because you have to make that explicit sampler type, you have to kind of plan on it from day one, right? Because we know that we're going to use virtual textures, so that's just the way things are going to be. You're probably also going to want to have separate default virtual textures, so like default virtual normal, default virtual color, default virtual masks, and make sure that those are like 128 pixels wide. Anything smaller and things get a little squirrely. The other kind of really big consideration with virtual textures is that when you are building them, when you're building your materials with them, you have to keep an eye on this virtual texture stacks number. So this number is basically how many different UV coordinate combinations are present in the material. Because in order to figure out what page we're looking at in the book, we have to cycle through all the different books that the person might be viewing. So each stack is a different book that we have to visualize. So in this one, I've got 3 virtual texture stacks because I've got text coord multiplied by 2, this one's multiplied by 3, but then if I drag this one up over here, it's not going to change my number of virtual texture stacks because I'm reusing those normal, or those UVs. But then if I dupe that off and I say, oh, this should actually be tiled at a 4, now I've got 4 virtual texture stacks. So this is just a thing to keep in mind when you're building out your materials. I don't really have a hard and fast number. Do not go above this number, but it is a thing to keep in mind, and we'll talk about that in a little bit too. So the other thing to keep in mind, because I mentioned, and we've said this on multiple occasions, streaming virtual textures save you memory at the cost of performance. And I think when people heard that, they got scared. They said, oh my goodness, I can figure out how to mix stuff around in memory. I don't want to give up performance. And so they kind of shy away from it. They're like, no, I can't use this. I can't use this feature. But what we're looking at here in a static scene is gather requests. That's, hey, how many virtual textures do we need to look at? We've got feedback analysis, that's, hey, what pages are we looking at? And in a static scene on this computer, it's like, what, 0.25 milliseconds? That's perfectly reasonable. It's practically negligible compared with the value of the memory savings that you get on the GPU. And even as I drive through this scene a little bit, you're going to see, oh, we get a little bit more as we're moving stuff around. But ultimately, I personally think the benefits of virtual texture streaming outweigh the performance costs by a pretty significant margin. And as a sort of convenience to you, the little helper feature, if you want to convert your project to virtual texturing, it's actually kind of simple. We just right-click on the texture, and we can do this convert to virtual texture. Now, if you do this on like a Nanite mesh and you say enable Nanite, it just does that asset. But because we have to change the sampler type in the material, this process will go up to the base material, find the sampler and the parameter that is using that texture, and then it'll go down to all the material instances to find all of the other textures that are being used in that sampler, so you convert those to virtual as well. So we run that to buy myself some time, and you can see, even though I just clicked on this texture, this other base color also got affected because they're both used on that same sample parameter in that material. The other thing that I want to highlight with virtual textures is that or streaming virtual textures, is that in your project settings, if you go down to virtual texture, there's this auto virtual texture sizing value. So when you import a texture that is 4K or above, we automatically turn it into virtual, because the likelihood that you will see all of MIP 0 of a 4K texture or all of MIP 0 of an 8K texture is practically zero unless you are running on a full 8K monitor and the texture is right in front of your face, right? So we're like, okay, no, you definitely need to virtualize these. But I think this creates the false impression, much like when we came out with Nanite. Oh, Nanite is for high-resolution geometry. It enables high-resolution geometry, so it's only for high-resolution geometry. But that's not really true. Nanite is a really efficient rendering path. We'll talk about that in a second. So if it can be Nanite, it should be Nanite, because it'll run faster. Similarly, with virtual texturing, just because it's a 2K or a 1K texture doesn't mean you can't benefit from virtualizing that texture. So it's a thing to keep in mind. Because I think even in this project, a lot of these textures are just 2K. They're not that big. But they're still virtual, and that's going to have a major benefit to your virtual memory or your video memory allocation. Okay. The other one that we're probably more familiar with is runtime virtual textures. This is where we bake the landscape down into a texture, and then you can sample, instead of sampling every single layer at every single pixel, now you can just sample base color, roughness, normal, whatever, and draw that, and it's really efficient. But we do have to store that virtual texture somewhere, and we just leave it on the GPU. It doesn't even touch the CPU, doesn't even touch your hard drive. So we render that into the GPU memory, into memory in GPU, and then we leave it there, and then we can sample it there, which makes it really easy to have these really big sweeping landscapes with fairly high resolution textures, fairly high detailed materials without a major performance impact. And what I've got here is the r.vt.rvt.mip colors visualization, just because I want to show you, okay, this is MIP 0, and then we get a little further out as we're generating the feedback of what page are we looking at, what detail level of the page are we looking at, and allocating those accordingly. I don't want to belabor this too much. I think there are a lot of great resources out there about how to leverage runtime virtual textures. There's a couple things I want to highlight, though. So in 5.4, we've now added Nanite tessellation and displacement. You can use it on a landscape. It's an experimental feature. We'll talk about that in a second. But the nice thing is that we now have a virtual texture content for displacement. So all you need to do, make another runtime virtual texture volume, set up another RVT for displacement, set up your material, and you're off to the races. Still experimental, though. Just wanted to highlight that this exists. The other thing with runtime virtual textures is that what sometimes happen, and I think actually I was talking to somebody about this at the Dev Lounge yesterday, is that you use runtime virtual textures and suddenly everything's really blurry because you might have it, that volume might be covering a really big area. And we intuitively think, if my texture is blurry, I must increase the resolution. Number go up, resolution better, right? And so you go in and you say size of each virtual texture. Oh, that's only 256. That's too low. Why is that so low? That's going to give me really blurry textures. And so you crank that up to like 8 or 16 or something, and you max out the slider. And now you have a 1024 tile. But the thing is, this is kind of counterintuitive. If you set the tile size to 1024, that means the smallest size of a texture, of a tile in that virtual texture can only be 1024. But we already intuitively know that you're not going to see all, like a 1024 texture spread out over 100 meters in front of you is going to get mipped at various points along that distance, right? And what this also means is that if we need to update any part of the virtual texture, we have to do it in this whole 1024 instead of even a smaller tile size, like if we did 256 or something like that. So sort of weirdly, the number that we want to change is not the size of each virtual texture, because this is actually going to make our rendering inefficient. The thing we would probably want to look at is the size of the virtual texture in tiles. So how many individual tiles are we rendering in this virtual texture? So we can increase that quite a ways. That'll give us a fairly high resolution. But if we're doing this and we go, okay, we're going to go up to 4K, 400 or 4,096, 256 tiles wide. And you might be building some 16, 20, 30, 40, 50 kilometer open world, and this isn't going to cut it, right? 1 million pixels is not enough resolution. And so instead of necessarily starting out by raising the size of the virtual texture in tiles, what I would recommend instead is enable adaptive page table, which you can find under advanced. So if you don't see it, click advanced. Enable adaptive page table. And so what we've got for a virtual texture is a page table that points to all the spots in memory where that texture lives. Adaptive page table adds another page table of page tables. So it's like a virtual texture so that we can have an effective higher resolution without having to allocate all of the memory that we might need in order to hold a 16-kilometer open world in one go. Adaptive page table, that's the takeaway here. How we doing? We got it? Everybody on board? All right. Okay. But we gotta do a little creative accounting, because one of the things that we try and do with Unreal Engine, which I really appreciate, is we want to make it accessible. We want to make it easy for people to get into the engine, start building features, start building content, and feel confident in doing so. What that means is that some of the settings that we might have that are default so that those users can have a really good upfront experience might not make the most sense for a larger production or a more advanced user, but we have to make sure that evaluate world position offset is on by default, because if you drag a WPO material onto a texture or onto a thing in the world, you expect it to move. But that might not be the most efficient thing for rendering, You might want to turn that off. Similarly, with virtual textures, we got to do a little bit of creative math. So by default in the engine, the streaming pool for non-virtual textures is 2,000 megabytes. But if we look at this project, we can see that our required pool is only about 100 megabytes. And maybe we fly through the world, we do a little bit of evaluation to figure out what this is. But that 2,000 megabytes, that's a chunk on the GPU. And if most of it is sitting empty, we can probably lower that number, and we're not even going to see a screen message about, hey, you gotta, we're oversubscribed to the streaming pool, we're going to drop MIPS, whatever. I drop that down to 150, turn on screen messages, start streaming. I lowered that. I'm not getting yelled at by the computer, which is really nice. So that frees up, I freed up 1,700 megabytes just by one console variable that you can set in your default engine INI, which I think is really powerful. Because again, compare that with our virtual textures, our virtual texture streaming, right? I've got 150 megabytes, great, we're all set there. And then our virtual textures are only, 500 megabytes. So I only really, even though I originally allocated 2,000 megabytes for all of the textures, all of the non-virtual streaming textures, I can clamp that all the way down to like 600 megabytes, and I can make room for other stuff that I might need on the GPU. Now, the tricky thing with virtual textures is that instead of like the streaming pool size being set really high, we want to keep our virtual texture pool sizes as high as they need to be and no higher. And this was a little tricky to do in UE in 5.3, 5.2, and whatever, but we added a fun little thing in the editor in 5.4. Get that right, is we now have a project setting panel for the virtual texture pool. Because instead of allocating all of the memory for all of the textures, we have to allocate memory differently for each of the texture compression types, because those memories are laid out differently. Don't need to get too deep into it. But by default, we have this pool auto grow in editor, so that if you are using virtual textures, you're flying through the world, the system notices, hey, I'm getting a little oversubscribed. I'm going to bump this up for you. I'm going to put those new settings in this transient pool and say, hey, why don't you copy those up to the fixed pool? So the fixed pool is the thing that you're actually going to ship with. And this can be really helpful so that you can find the exact high water mark for your virtual textures. But maybe you're starting out and you're like, well, that's not really that helpful. I don't need it on for all of my users. Maybe you turn it off. You have one tech artist go in every couple of days, fly through, make sure the settings are right. Or maybe even at the start of the project, you're going to say, all right, why don't we increase our default pool size to 48 megabytes or 64 megabytes? It's going to give you a little bit more, allocation on the GPU, but maybe it makes that sort of default experience a little easier for people that are going through the world. Because what can go wrong if we don't If we are oversubscribed, if we try and fit more water in the pool, is we have to get water out of the pool, or we have to take the stuff that's in the pool and make it smaller. So you end up with blurry textures, right? We've all seen this, right? Yeah, we all know what this looks like. So this is what it looks like when things go wrong. And what we can do to kind of figure out, all right, what's going on, where are all these textures coming from? We added a new thing in 5.4 as well called the render resource viewer. And this is everything. This is not just your old statistics panel with textures. This is showing you your buffers. I can see, hey, what's my TSR color history buffer? 84 megabytes. This is all the stuff that's on the GPU. And I can go through and I can see I've got virtual physical texture. These are all of the different compression types. And so in the project settings, I've got it set to 32 megabytes by default. Great. I've also got this virtual page table. That's kind of the thing over everything. You notice these are not labeled. I had a fun chat with our engineer who's overseeing this. He's going to see if we can fix it for 5.5, make it a little more useful visualization. But this is really fun. We're going to come back to this. And then the other kind of thing I want to talk about on the performance side of virtual texturing is that CPU cost, that feedback. And so what we're going to do, we upload new textures to the GPU at a certain rate every frame, and that there's 2 numbers for that. And don't worry about trying to see that tiny little CVAR thing. It's going to be in the links at the end of the show. Is r.vt.max uploads per frame. So this is going to affect both runtime and streaming, but we actually want to keep the RVT uploads low, but we might want higher streaming virtual texture uploads, so we can do an r.streaming uploads, and that's going to help a lot there. If you start to see, like, when you're flying through the world and the textures aren't coming in as quickly, that's because we're not able to upload as many textures to the GPU in a single frame. So that's the console variable. The other kind of funny thing that can happen with virtual textures is when we're doing this feedback pass, we are looking at 1 pixel within 16. So every 16 pixel square, we're going to look at one of them to figure out what MIP, what tile should we be loading up to the GPU. And we're going to flip through the whole frame, and we're going to do that set by r.vt.feedback factor. But the pages that are stored in memory have a timer on them. So as our little blue dot of feedback is going through and looking at all of these textures, all of these little textures have a timeline before they get evicted. And that's set by r.vt.page threshold, or page free threshold. So that's a number of frames where we haven't seen a texture where we're like, okay, you're done, you're 86, get out of here. But that might not work if we have a lot of virtual texture stacks, if we have a lot of individual unique virtual textures. You might end up in this weird situation where the feedback pass isn't hitting every texture, every frame, and so things are getting evicted. And the way you're going to see this is if we go to stat virtual texturing, you're going to see this map requests number get really, really high in a static scene because it's constantly trying to upload new frames, right? Because we get evicted and then we see at the next frame, oh, we got to send it back. That's not really efficient. We don't want to do it that way. Okay. Taking a little breather. All right, so streaming virtual textures, we're all good, right? We're going to turn them on when we go home. Great. Okay, so let's talk about Nanite. Nanite is virtualized geometry. It's called virtualized micropolygon geometry, Nanite for fun. And really quickly, right, we all know Nanite. We get near pixel perfect lotting of our geometry. And what that means, this is really important to understanding Nanite, is that even though you might have on disk 10 million triangles and you drag that into the world, that doesn't mean we are rasterizing 10 million triangles, because we all know that that's inefficient. So instead what Nanite does is when it will simplify that mesh down, it'll break it up into clusters of 128 triangles, and then it'll break up clusters into subclusters and subclusters and subclusters until we have like a MIP 16 of a piece of geometry. And we stream in the clusters that we need based on the feedback. How many pixels per edge should we be rendering? Those are just tiles. Those are just the same thing as virtual texture tiles, right? Clusters tiles. And as an aside with Nanite, if you were using Nanite, highly recommend using virtual shadow maps. Those two go together like peanut butter and jelly. There's a couple of new things that came on with 5.4 that I wanted to call out. Some experimental stuff, some new things that we've learned. And the first is Nanite spline meshes are now production ready. Chris mentioned this in his talk on yesterday. But what I've got over here is I've got a little spline blueprint. And I'm going to go into our modeling mode. I use this draw spline tool, and I can click on my little, got ahead of myself. I can click on my little spline blueprint. I can draw spline, use existing actor, and now I can draw really easily a spline that'll fit to the terrain as I'm drawing it around. I can hit accept. And then if I go into our Nanite visualization, I can see Nanite mask. It is a Nanite spline mesh. That's great. It's going to render more efficiently. Everybody's happy about that. One quick aside on Nanite spline meshes is that for various reasons, make sure that the material you apply to it is only applied to Nanite spline meshes. Some things happen with the usage flag that get a little interesting. So have a underscore Nanite spline version of your materials. The other fun thing that we've got now in 5.4 that you've got access to is Nanite tessellation. So this is still very experimental. There's a lot to figure out with performance and tuning and balance and things like that. And generally speaking, this is a sometimes food. While it would be fun to have Nanite tessellation on every single thing in our scene, it does increase our cost of programmable rasterization, which we know is going to be more expensive. But there are some memory benefits to having, to using tessellation. So in the scene, I've got two Jersey barriers that I picked up from Quixel Megascans. And on the left, we've got the Nanite resolution version. And on the right, I've got the medium resolution version. But if I turn on tessellation, you're not going to see a huge difference, but if I go into the Nanite triangles view mode, now we've got a lot of extra detail in that mesh, and all we had to pay for that was maybe a 1K or a 2K displacement map. So, fewer triangles on disk with a little extra texture, you might be able to get a little bit of savings on your disk size. The other fun thing that we added in 5.4 is this lerp UVs checkbox in the Nanite settings struct of your static meshes. So by default, Nanite will, when it simplifies that geometry down to make those new clusters, it will take all of the attributes of those vertices and interpolate them to whatever, percent value is needed. Generally, this is desirable for vertex colors, for normals, or something like that. But if we wanted to do something like vertex animated textures, we need an explicit UV coordinate that we know isn't going to be wandering around our vertex animated texture. So you can go into your settings, disable lerp UVs, and what you get when you maybe go through the very experimental anim to texture plugin is a crowd that is all Nanite and animating, which is really fun, right? So I set these up with our twin motion characters. I use the anim to texture plugin to generate the animation and drive it. You can do it whatever you want. The takeaway is now we can do vertex animated textures with Nanite. As a quick aside on the characters thing, we'd want to still keep these at kind of current gen skeletal mesh resolutions, treat them like they're non-Nanite, because the cost to rasterize these, the WPO material, that can get a little expensive. So we want to keep our triangle counts pretty low on these. All right, so that's an opt-in feature. This one's on by default. So at GDC 2024, my colleague Graham Wildahl presented Nanite GPU-driven materials. An excellent talk. It'll be in the links at the end of the show. No action is required on your part for the first part of this, because now with this, Nanite shading is done through compute shaders. We're finally shading with compute shaders, which is great. The benefit to you is that now we don't have to pre-allocate shading bins on the GPU. Those empty bins, if you don't see a material, it's never touched. We never have to rasterize it, we never have to shade it. We never have to go look at that thing and go, oh, this bin, what texture, what pixels do we need to render? None, great, move on. That step takes a little bit of time on the GPU. Now we don't have to in 5.4. The other fun feature that we've got that came along with this is variable rate shaded Nanite. So now we don't have to shade every single pixel in a 2x2 quad at each time. We can shade a whole 2x2 quad or a 4x4 quad or something like that, because we know that the rate of information isn't necessarily changing across that surface. There is an important consideration, though, which is that you cannot have derivative ops, so ddx, ddy, in those materials, because if we have derivative ops, then we can't variably rate shade everything. And there's a couple of new visualizations that I think are really fun that I wanted to call out. So we can do r.nanite.visualize.advanced1. And that's going to give me a few extra view modes. One of them down here is no derivative ops. So derivative ops are going to mean we can't variably rate shade. So here's a little visualization that is showing you where ddx and ddy are being used in those materials. Super handy. The other fun new view mode that we've got is not buried under advanced. It's pixel programmable. And this is showing you all of the textures or all of the materials that are masked, that are PDO, that are nanite displacement, so that if you're driving through the scene, you can pick these out really easily. And with nanite, though, there comes some pipeline challenges, right? There are a lot of polygons that we have to consider, and sometimes our DCC apps don't really like that, or we have to find new and creative ways to use nanite. So there's a cool thing that we can do when we have a lot of vertices, is we can embed information in them. So for example, we might embed something like curvature in the alpha channel of our vertex colors, and we can use that to drive a material blend, and we can rust out these cars. And I did all this with these cars in the hillside sample with a little simple geometry script to bake the curvature, blur it a little bit, judge the values. That's all I really needed to do. Now the thing is to keep in mind when we are baking information into our vertex colors, the rate of change of that color shouldn't be too great. Like, we don't want to bake a really high resolution Perlin noise into our vertex colors, because when we're generating the clusters, when we're trying to simplify the mesh, if we look at one pixel or one triangle to the next and we see, oh, there's a really big delta in the UV values or the color values, well, that's probably a border, so we're not going to simplify that down. So curvature is great, really nice and smooth. Ambient occlusion, great, really nice and smooth. Perlin noise, don't do it. The other thing with nanite, and this is a really big one that I want to hammer home, is the fallback mesh, right? So if we're targeting non-nanite platforms or we're using hardware ray traced lumen, that fallback mesh is really important in order to render things efficiently. And what I see happen a lot is if we go and we grab our mesh and we look at it and we go, okay, I might have a fallback target by default. This is set to auto. And what we will probably do, because this is an intuitive value, is we will use the percent triangles, right? I know what percent triangles means. If I set this to 1 or if I set this to 10, it will scale it down to 10% of the source triangles. But if I've got a Quixel Megascan that's at 1,000,000 triangles and I set that to 10%, that fallback mesh is still going to be 100,000 triangles. And if we think about that on a previous gen, a non-nanite platform, 100,000 triangles is still a lot for a rock, right? So instead, what I would recommend you use is relative error. And relative error is a little harder to intuit because I don't know what that means. But it's basically how different from the source mesh should the fallback mesh be based on Nanite's calculations. So I might set this to a uniform value across all of static meshes in the scene. And what that means is that because we're looking at difference and not triangle numbers, I've got my Nanite 100 million triangles, I've got my medium 50,000 triangles. And if I use relative error instead of triangle percent, right? Triangle percent, this is the same triangle percent number, but these are two very different fallback meshes. But if I use relative error instead, I get a more consistent and uniform distribution of triangles across the surface. So if you're looking for a way to sort of automate a baseline for all of your meshes in the scene so that you get a consistent fallback mesh, you want to be using relative error instead. Of course, all these triangles have to go somewhere on the GPU, right? It's not just free, and that is in the render resource viewer. So I can go back to our old friend, the render resource viewer, and we can see up here the Nanite Streaming Manager cluster page data. This is Nanite. This is where it lives. And we can see, if we go to stat Nanite streaming, I can see the number of resources, the number of root pages, it's the number of books, if you will. There is a hard cap of 49,152. There's a hard cap. But what this number means is the number of unique Nanite static meshes in the scene. If you hit this number, call me. I'd be really interested to see what your scene looks like. And we can come down here, we can see that pool size, right? We set a pool size. How big of a pool can we fit all of our Nanite memory into? So that's going to be a total of 608. And I can come down here to the visible streaming data size in megabytes. And I can see that I'm only uploading about 150 megabytes of data to the GPU for Nanite purposes. So maybe if I wanted to have something else on the GPU that takes a little bit more room, maybe I can bring down my Nanite number. But if we do that, similar to if we lower our streaming pool size or our virtual streaming pool size, we get blurry textures. Well, if we can't fit all the clusters that we need into memory, we get lower resolution, we get blurry geometry, right? Same kind of thing. There are a couple of project settings that I wanted to highlight in the Nanite world. So when we're trying to look at our memory savings, one of the things that we can look at is this support reversed index buffers and support depth-only index buffers. These are project settings you can set. You can also set them in device profiles, so they can be a cook time optimization. But basically, we take the vertex order of the mesh, and we store a reversed version of it so that we can more efficiently draw something that has negative scale. But I don't really recommend building your worlds with negative scale. There are a lot of reasons I don't recommend it. So maybe we don't want to do that. We can turn that off. Because, again, going back to the render resource viewer, our old friend, if I scroll down here, we've got the truck, and it's got a wireframe version of it, and a depth-only reversed version of it, and a reversed version of it, and a depth-only version of it. But this is not for Nanite. Nanite doesn't need this data. It's for previous gen consoles. It's for non-Nanite platforms. So instead of having, 5 times 32 megabytes of data to store this truck, maybe I can lower that down. I can turn those features off, and I'll save myself a bunch of extra space. So if you're targeting non-Nanite platforms and you really do want to build your worlds with negative scale, you do still need to leave these on. But if you're targeting fully Nanite platforms and you know you're going to build your world with negative scale, you can turn these off, save yourself a bit of room. Whew. Almost there. All right, last one we want to talk about today is virtual shadows, virtual shadow maps. Kind of similar concept to runtime virtual textures. We store all the shadow maps up in the GPU addressed by a page table. And we can see, even if we go to a virtual shadow map, virtual page, right? Each of these is a tile that's stored in memory that's addressed. We've got some clip levels so that we're maintaining a really consistent resolution as we go forward from the camera. And the really nice thing is that with this technique, we can cache these virtual pages. So if we don't need to update them because the shadows haven't changed, we don't touch them. It's great. That can be a really efficient rendering technique. Just a couple of updates I wanted to call out, and we'll get to some memory stuff in a second. The first is that there has been a change to the way we handle static and dynamic caching. So from 5.0 to 5.3, if a static mesh ever invalidated cache pages, it was always treated as dynamic. And by default, there are two sets of virtual shadow maps, the static and the dynamic. So if the static stuff, it doesn't really change that often, we can just leave it where it is. And then the dynamic stuff, we know we're going to update that. So we can only draw the dynamic stuff into the dynamic pages and then composite them together. But if you move toward a tree and it starts invalidating cache pages, and then you move away from a tree and it stops invalidating cache pages, for various reasons, that tree would always be treated as dynamic, which isn't ideal. So we fixed it. There's now a console variable r.shadow.virtual.cache.static separate.frame static threshold, and that's basically how many frames before we evict a dynamic mesh from the dynamic pages and we send it back to static. There's another fun change that happened with the way we handle WPO disable distance to, again, make things feel more intuitive, right? So WPO disable distance is really great. So I've got my Ferris wheel here, and it's animating with world position offset. And if I move away from it, I've got a really aggressive WPO disable distance set on it. As we move away from it, it stops moving. It stops animating, right? That makes sense to us. It's too far away from the camera. But what happens if we're really close to it and it's casting a really long shadow? What if it's dusk? What if it's dawn and it's got this really long shadow? Well, up to 5.3, what would happen is that would invalidate all of those cache pages potentially out to the horizon. That doesn't make sense. That's not intuitive. That's not really how we want to live. We would expect that the WPO disable distance will also affect the range at which a cache page no longer is invalidated by something close to the camera. So, like I said, we fixed it. There is r.shadow.virtual.clipmap.wpo disable distance.lod bias. And what that does is it says, so we saw earlier, right, we've got our clip levels. Go into our virtual shadow page, we can see our clip map MIP level. So this is kind of, you could think of these like cascades. So the LOD bias for that basically means that take the WPO disable distance, bias out a certain number of clip map levels, and beyond that distance, don't let this mesh invalidate cache pages. It's a really good efficiency. I'm going to exaggerate this for effect because I want you to know what this looks like in case you ever run into it. So if we instead r.shadow.virtual.clipmap.WPO disable distance.lod bias, by default this is 3, so take the WPO disable distance, add 3 clip map levels, don't invalidate after that. I'm going to set this to 0, and I want you to look at what happens to the shadow of the Ferris wheel. So hopefully you can see this, but the top half of the shadow is not animating because this has a WPO disable distance of like 2,000 units. So at 2,000 units, we get to that clip map level, don't invalidate cache pages, and you get this discrepancy. You get this tearing in the shadows. So like I said, the default value there is a LOD bias of 3. Likely you're not going to run into it, but if you ever see a situation where like half of your shadows are animating and the other half is not, this is what's happening. Hopefully you don't run into it. If you do, give me a call. But again, this is memory that we have to put somewhere. It has to go, it has to be somewhere, and we have some opportunities to manage it, right? So I go back to our old friend, the render resource viewer, and we've got our shadow virtual physical page pool. This is how much memory the GPU needs to store all of those virtual textures. Well, on the GPU, we have the static cache pages, the dynamic cache pages, and we have a number. So I could say like r.shadow.virtual.max physical pages. So max physical pages, that's, again, how many tiles we have of this texture. By default, it's 4096. But maybe I've got a platform that doesn't have a lot of extra memory, and I want to lower this. So in my device profiles, I might set this to 2048. So, and if I refresh the render resource viewer, we now see, oh, I've cut my shadow page allocation in half, down to 256 megabytes. I just saved you 256 megabytes for free. Shadow resolution, but we'll get to that. And then the other consideration, the other thing you can do to save yourself a little bit of memory with virtual shadow maps is r.shadow.virtual.cache.static separate. So I mentioned earlier, right, we've got a static page and a dynamic cache page. But if we have a dynamic time of day, we know that we're always rendering all of the shadows every frame. So it doesn't make sense to have a separate cache for static things versus dynamic things. So I can turn that off, and now I can my shadow virtual page pool down to 128 megabytes because I already know that I'm not going to use half of that memory. So dynamic time of day, you save yourself a little bit of memory by turning off static caching. Okay. Did it. We got there. All right, so what have we learned today? Well, we learned not to scream your voice off at the opening night party. We learned how to set up virtual textures and tune our project's memory allocation accordingly. We learned what improvements to Nanite, like spline meshes, experimental features like tessellation, how we can investigate and utilize Nanite memory, and we learned how to debug issues with virtual shadow maps, and what we can do if we need to tweak the memory overhead of virtual shadow maps. There are a few more talks today that I wanted to highlight so that you don't have to listen to my poor voice anymore. There's maintaining top quality content, Unreal Engine content for virtual production at 10:30, as well as my colleagues from Japan are presenting TSR, Nanite, Lumen, VSM, UE5 graphics, features, insights from Japan. And then Weta's going to talk about the war, the art of the war is over. I just think it's a fun art thing. And finally at 4 o'clock, you're probably lighting wrong because I light wrong, and I'm going to go to that talk, so I'll see you all there. All right, on that note, I've got a little bit of time for questions, and this is a QR code. It'll take you to my link tree with a link to a dev community article with all the links from all the stuff that I referenced in this show, and I'll probably add more to it as we go. So thank you all very much. Don't forget to fill out your surveys at the end of the show. If you liked the talk, remember my name is Matt Ostale, and if you didn't like the talk, remember my name is Chris Murphy. All right. Dean's got a microphone for questions, so if you've got a hand, I've got one up over here. There's one right next to you. 1, 2, 1, 2. Go ahead.
Sorry, I've got to find my question. So thanks for the talk. It's really, really interesting. So why virtual textures, why isn't that on by default?
Yeah.
And why is there an option to change virtual texture size?
Yes.
If you're saying you don't want to be this big.
Yeah. So you can change the memory allocations, right? I think that the thinking is that it's not on by default because it is kind of an advanced feature. We have to put a little bit more consideration into it, and you need to do it intentionally. And if you kind of go into this and you're like messing around with values that maybe you don't understand, I've done this myself on projects. I'm like, virtual texturing, and now everything's blurry and I don't know what to do. It's a little tricky to get set up and running. It's not as easy as Nanite where you just enable Nanite and you're off to the races, right? So it does require a little bit of setup. I think there's some discussions about, hey, what could we do in the future to make this feature a little bit easier? If you have used virtual textures on your project, I would love your feedback on like, how was the process to set it up? Did you run into any challenges? Take that feedback back to the team, make the engine better for everybody. Hopefully that covers it. Cool.
I've got a microphone, I'm going to talk as well.
Great.
Don't use it for virtual production. Because you want full control over exactly what the textures look like. Yeah.
I think even like movie render queue turns off texture streaming by default. Yeah. Don't turn off texture streaming if you're real time. All right.
Yeah, I'm an artist, so apologize if I.
You're great.
But what's the difference between sparse spineless texture arrays and virtual texturing if you're doing something for a switch or like a low end system with?
There's a few questions in there.
Yep.
I'll take a couple of them at the Dev Lounge this afternoon.
Yep.
Sparse volume textures. So this one's a little tricky, right? Because they're both SVT, but streaming virtual textures and volume texture, two different things.
Yep.
Kind of similar concepts. I personally haven't dug into sparse volume textures a whole lot, but that's more for like doing volumetric effects and streaming, different frames of a big volumetric effect that you might have baked out of something like Houdini.
Yeah, I was thinking for like bindless textures, like bindless texture.
We will talk about bindless at the Dev Lounge.
Yeah, cool. All right, sweet. Yeah, I was just curious because we've got memory issues at the moment. So yeah.
Yeah.
Cool.
Yeah, we'll talk about bindless later. Great. I've got one over there and one over here.
This one's closest.
Thank you for sitting at the footing. I'm sorry.
With the runtime virtual textures, I think at the moment there's no support for emissive. Is that something that is coming?
I don't know, but do you need your specular or anything?
Yes.
Okay, well, that would be a little trickier. The thing with RVTs is you can always add more volumes and set up another RVT for like, just set it to base color or YCOG or something, and use that, have another one that you can draw to. The only tricky thing is that your runtime virtual texture output won't have, you can't switch it, right? You can't say, if you're drawing into this RVT, do this. If you're drawing into this RVT, do this. So maybe we jam on this in the Dev Lounge later.
Sweet, thanks.
Cool.
The first person actually kind of asked my question already, but
Great.
the first, when you enabled it on the texture, it did actually ask you for a value at the bottom left, and it was something you didn't really talk about. Is that actually setting the texture size there?
Yeah,
Is that
yeah. I know what you're referring to. So if I go into this and I say convert to virtual texture, this is the one you're talking about?
Completely.
So this is the size threshold, and it's gonna, if you have a 512 texture that's referenced parameter, it won't get filtered. And you're like, hey, maybe I don't need to make all of these virtual. Maybe I find a better way to use this. So that's what this is. It's not saying clamp this to this value. It's saying only convert to virtual at or above this value. Make sense?
Yeah. Thanks.
Yeah. So like if I set this to 4096, these aren't 4096 textures, so they're not going to show up. So.
Hey, you mentioned about setting the streaming pool size or the fixed streaming pool size to just the right amount of size that you mentioned. Is there a way of controlling that per map, or is that per project? Like
this would be like a per project value.
Right.
Basically, so one of the reasons that you might be struggling right now is if that auto grow in editor is turned on every time auto grows, it's gonna hitch a little bit because it has to reallocate a bunch of stuff. So if you're changing it, like I wouldn't change necessarily on the fly. I kind of like, all right, I kind of know what this is going to be. We could talk about some other controls for bias on a per device profile basis.
Yeah, for sure. We use linear content, and there's some maps where I guess we don't necessarily have to set it so big, like very light maps where we just can set it smaller, and other maps where we need it quite large. But by the sounds of it, you can just set it per project. It would have to use a larger size.
I would set that one on a per one object basically, because I'll turn this question to you. What do you need that extra memory for? Like, do you have a scene where you're like, oh man, I really, this scene I need more distant memory, or scene I need more shadow memory, or something like that. Like, and you're trying to push and pull.
Optimize, like not having to give that extra memory for maps that don't need it.
Sure. Yeah, I guess really the question is, what are you going to do with the memory that you're saving?
Right.
Something to think about. Cool. All right, I think that's time.
Oh, one more.
One more, and then more in Dev Lounge.
Hello,
later.
thank you for the talk. I think it's just it's not a question; it's more like a feedback you asked. So it also may be answered why it's not enabled by default, because there's some kind of issues engine. Like for instance, if you calculate HLOD, it doesn't wait all tile loading, and sometimes your HLOD become blurred.
Oh,
And
yeah.
also, if you calculate the whole partition minimap, which we use in runtime as well, so also they didn't wait for the tile loading, and your minimap become blur.
So
I can continue.
yeah, we'll chat about this later. The thing that I totally forgot to mention, you can use streaming virtual textures to draw into a runtime virtual texture. Really important thing that gets missed a lot, because the RVT draw has no feedback paths, so we don't know what MIPS to pick. So if you're putting a bunch of textures into your RVT draw and they're all looking blurry, even mini maps or HLODs aside, if your RVT looks super blurry or weird or patterned, you can't use virtual textures in your landscape material.
Yeah. Also, the UI you cannot use virtual textures.
Yes, I believe so. But it would be the one to talk to about that. Cool. All right. Thanks everybody so much. I really appreciate your patience.